Okay, so it's really great to have Mohammed here. I just was introduced to him through John Shopland. I think many of you guys know John. John was in Penn for many years, and then he moved to Michigan. Mohammed is working kind of in a parallel universe with us. He's developing a variety of highly innovative sources. His background is in electrical engineering. All of his work, his bachelor's, his master's, and his SCD are from MIT in electrical engineering, where he's specialized in a variety of different innovative optics and photonics devices and components. He joined Michigan right after graduate. Well, no, he went to Bell Labs and worked for actually about 7 years at Bell Labs, and then went to Michigan after that, became an assistant professor, and he's worked his way up through the ranks actually very quickly. He's now a full professor. He's also appointed in biomedical engineering, electrical engineering, and internal medicine. So you can ask him some questions about internal medicine. But I think that appointment is really kind of one of those classics to help bridge School of Engineering with the School of Medicine, which Michigan is doing actually extremely well. Has kind of initiated an innovative program to introduce engineering into their medical school curriculum. He has an extraordinary record of invention, creativity, and accomplishment. He has over 140 patents, which when we were talking, and I was wondering, that's just an amazing, that's an incredible output and quite unusual for academics. Many of the designs of supercontinuum sources that are out there and being used in the field, in defense and security, are the designs that Mohammed has developed. Of course, he's also quite prolific in publication in peer-reviewed journals, and has won a number of really outstanding awards. So we're really lucky to have him come on such short notice. We just kind of put all this together in the last couple of weeks, and we're very hopeful that with the sources that he is developing, which are really quite spectacular, we'll be able to establish some interesting collaborations in biomedical, both basic science as well as applications. So let's welcome Mohammed.
Thank you. Well, Bruce, thank you very much for the invitation. We all appreciate all you coming, and of course, thanks for the pizza as well. Like all academicians, I have plenty of slides. Slides are like our, protective blanket. We got to have it, and so we got plenty of slides. We don't have to use them all. I'd much rather have an interactive. If you got questions, raise your hand. If you get something out of the talk, I'd much rather have that than go through all my slides. If you have questions, please stop. It's a mixed audience, Bruce tells me, which probably means you know more than I do. And so on some of those questions, I'll punt to you and say, what do you think? That's the usual response on that. So as Bruce said, I have joined appointment in electrical engineering and also in internal medicine at University of Michigan. We also have BME and applied physics along the way, but those aren't the major ones. One of the things we've done at Michigan, by the way, they bought the old Pfizer facility. It's now called North Campus Research Complex, which is dedicated to sort of translational research. So those of us in the med school who don't have clinical practices actually have offices and some labs in NCRC, North Campus Research Complex, to help to kind of bridge that gap. And I'm also the founder and chief technology officer of Omni Sciences. You see some of the lasers that we build. Obviously, when we do benchtop stuff, we do at the university. But when we need to build prototypes, particularly for the Defense Department, Omni Science handles that. And then what we're really looking at the medical applications in Omni MedSci. So I'm a fiber optics and lasers guy. And so what that means, up through 2002, I was basically a telecom guy. And so ask me about telecom, I'll be able to tell you everything. But then after 2002, when the bubble burst, I still use the same technologies. Everything here is telecom technologies, but it's telecom for anything but telecom. And so the two applications are really in defense and healthcare. Defense, why? Because Defense Department, unlike NIH, will pay for the laser development. And so we've actually built most of these lasers for the Defense Department. Obviously, they want to go higher and higher in power, higher and higher in performance. Cost is not so critical. But they're looking at applications, and I'll talk a little bit about it, in more intelligence agencies identifying targets based on their chemical signatures. But we see really the application and the purpose of my coming down here are really on the medical space, where we think really the commercial applications and the the life-changing applications can come. Things like breast cancer, diabetes, other things. And I'll tell a little bit of the experiments that we're doing there. But having said that, I just give the talks. The rest of the guys do the work. So a list of some of the collaborators. The folks in the first row are actually my students or colleagues. We also work with folks in BME, med school. Omni Sciences has its own crew as well. And actually, I won't speak so much to the lower part here, but most of our defense work is done with SAIC, what used to be SAIC, now Leidos, and almost all of the field tests. Most of our lasers have gone through field tests, and those are usually performed with either NGA or Wright-Patterson Air Force Base. Again, a lot of folks on those things. So again, what I hope to cover, but please, again, feel free to stop me, ask questions, is first a little bit about the lasers themselves and how they operate and why it's a platform for various wavelength ranges. And then I'll show you as an example how we've built different prototypes. Again, all of these have been really for government purposes. And again, give an illustration of how we've taken that basic design and turned it into prototypes that have different kind of specifications. And bottom line is, if anything you want, we can build. So, you can build certainly the visible. We don't do visible because you can buy them commercially. We'll tell you where to buy them. But if we go 1 micron and beyond, that's our space where we do it better than many others, we think. I won't, because of the shortage of time, I don't think I'll focus so much on the field test results, maybe just summarize sort of the key findings in those. And that's really more by way of validating that these lasers really do work. They've actually performed in field tests in government laboratories. And I'll just touch on 2 of the ongoing projects in our laboratory. And so these are not work completed, but they're ongoing. One is on diagnostics, in particular non-invasive glucose monitoring. And one is more on the therapeutic side, where we're removing visceral fat to treat diabetes. And again, those will be by way of the example of the kind of things that we can do with the lasers that we develop. So a lot of the work we do are what are called super continuum lasers. Super continuum lasers are really a sort of a... There goes the sun. Yeah. Supercontinuum lasers are really a crossbreed between a lamp and a laser. It's like a laser in that it provides a nice spatially coherent beam that can propagate for a long distance, but at the same time it covers several octaves of light, and so in that sense it's like a lamp. In the case of a lot of the military stuff, well, we're replacing what he just shut the window on. We're trying to replace the sun. For a lot of spectroscopy they do. And a lot of things that you guys are doing here, you're using halogen or tungsten lamps. This, for example, could be a replacement for some of those lamps. Bob Alfano wrote an article in Scientific American a number of years ago where he called it the ultimate white light. Bob has worked on it for many more, I think more years than I've been alive probably. And yeah, he's the grandfather of it, but we've done some things differently. And these are the key differences in what we do. Number one is, again, most of the early work in supercontinuum has been in the visible, or maybe near infrared. We have extended the wavelength range mostly into the mid-infrared, so we simultaneously cover all the way from about 0.8 microns out to 4.5 microns, and we'll soon go out to 5.5 microns and eventually down to 13.5 microns. Key is almost all of the commercial units that are sold, and certainly all of the early work on supercontinuum used what are called mode lock lasers, usually large or expensive lasers. We have replaced all of that with off-the-shelf telecom parts, what are called COTS, commercial off-the-shelf parts. So literally we use parts that are often used in your telephone network in these lasers. And actually, this is an old slide. We've scaled the power. We're up to 64 watts and beyond. The next gen will be about 100 watts. Now, again, I don't think you need that for a lot of the medical applications, but for the defense applications, it's going toward higher power. And we have a simple way in which, without changing the architecture, you can scale the power of the laser. So it has a lot of flexibility in that sense. So let me explain. It's actually a pretty simple system. And so you should be impressed by the simplicity, not by the complexity of it. And it really is quite simple. We start off, it's what's called a MOPA configuration. This is almost all of our laser, or basically of this configuration. We start off with the laser diode, DFB, laser distributed feedback laser diode. Just like when you pick up your landline, your voice gets encoded onto DFB before it goes cross country. Same type of laser diode here that we use. Well, but again, if I have, let's say, an iPhone and I want to drive a speaker, there's not enough power coming out of this. So what do I got to do? In the case of the iPhone, I've got to go through an electrical amplifier to boost up before I can drive the speaker. Well, likewise here, there's not enough power out of the laser diode to do the supercontinuum generation, so we boost them on what are called optical amplifiers. Standard stuff, just like if I'm calling from Michigan to Irvine, every 80 kilometers my voice gets too weak and it's got to be boosted up again using optical amplifiers. So again, standard stuff there, usually multi-stage depending on the power that you want. So all of this is standard off-the-shelf, telecom 101. Nothing new there. We're not, we do it cleverly, but not really any different than anyone else. So what's our secret sauce? Well, it's a piece of fiber. So we use about a 1 or 2 meter length of standard single mode fiber. Believe it or not, that's the magic. Followed by, you choose the fiber you want depending on the wavelength that you want. And it actually turns out this is quite profound. So yes, the solution is about 20 cents worth of fiber, or maybe $2 if it's really expensive. And that turns out to be the magic, because what we're really doing is we don't use mode locking, but we actually use the natural physics of the fiber to generate the supercontinuum. Let me illustrate that. So what happens is when I go into this standard single mode fiber, and by the way, we don't usually put a fiber in there, it just happens to be the pigtail of the pump combiner that you're using. Well, in there you undergo something called modulation stability, which ends up breaking up the pulses, and then basically go into nonlinear medium, which we use as fibers, to generate the broadband light. So what happens is that when I go into this 1 or 2 meter length of standard single mode fiber, I'm going in with typically around half a nanosecond to maybe 2 nanosecond long pulses. That's what's known as quasi-CW pulses. And we're at peak powers that are in the kilowatts and in a region that's called anomalous dispersion region. Well, it turns out in that regime, these quasi-CW waves are unstable. And it's actually trying to break up into something which Gordon can explain to you if you don't know, are called solitons, because this natural solution of the fiber are what are called solitons. And so when you put this broadband, I'm sorry, I'm trying to skip around this display, but when you put this sort of broad pulse in, just through noise, typically just the amplified spontaneous emission from the amplifiers, it will try to break up into these pulses that are known as solitons. And those solitons will actually start to collide with each other. So for example, if I go down the fiber, you'll start to see these pulses colliding. Here's the key point. By using this natural piece of physics in this 1 or 2 meter length of standard single mode fiber, I get the effect of basically having mode lock laser. And so whereas with your Fanium laser or your NKT laser, they go through elaborate schemes to mode lock the laser, we just replace that with a 20 cents piece of fiber to do that. Yes, let me go one more slide and come back to you. Sorry. I know I invited the questions, so I will take them. But this gives an illustration of this, just some simulation to illustrate. This is the time domain, this is the frequency domain. And so here we're showing, for example, a broad pulse. And as it continues to go down the fiber, you can see that the solitons are developing more in the higher intensity part of the pulse. And in the spectral domain, what's happening, you're generating sidebands and more sidebands. And if you continue to allow these pulses to go down the fiber, you find that they start to collide with each other, run through each other, and generate these super pulses that are about half a picosecond wide. Again, the key point being that I don't have to work hard to get a half a picosecond pulse, but I get my half a picosecond pulse just through the natural physics in the fiber. So you had a question?
Yeah, what terms the temporal pulse separation that you can call the repetition rate?
Well, that will depend. I didn't plant the question, but since you asked. So there is a knob here of sorts. So one of the reasons that this laser scheme is scalable in power is, again, we start off with nanosecond pulses from the laser diode. What it means is we're just using a laser diode naturally as it wants to be pulsed. And for getting the spectral width that I want, I need to have a certain peak power. So I amplify those pulses to get the peak power I need to get the spectral width. So the spectral width is set by the peak power. But there's no memory in the fiber, and so one pulse doesn't see the next pulse. And so I change the repetition rate to get my time average power. So if I have low repetition rate kilohertz, I may have 20 milliwatts of power. As I go toward a megahertz, I get watts of power, and as I go to higher repetition rate, I get more and more time average power. So peak power is set, the amplifiers, if you like, are set to get the spectral width, and then the repetition rate is adjusted to get the the time average power that you want. So it's actually just a knob on the laser that you can change to adjust the power, and I'll give you an illustration of that. And so typically we're in the megahertz range is the simple answer, but again, depends on the power that you want. Sorry, Bruce?
Is that just done by direct current control of the laser diode?
Yeah, we just, the driver to it, we have electronic driver that we just change the rep rate. Now, mind you, if you want to keep the same spectral width, you also have to adjust it so that, so what we do is we change the rep rate, but you also need to change the amplifier so that you're maintaining the same peak power, because the spectral width is set by the peak power. So you have to, you have to adjust it in a way that you're keeping the same peak power coming out of the laser system.
How fast do you typically drive the laser diodes?
We're typically running in the megahertz range. For the couple of watts of power, it's in the megahertz range. You'll see the numbers for some of the units that we have, but it's on that order, around the megahertz or so. So we're typically talking about 0.5 to 2 nanosecond pulses in the megahertz frequency range. Now, mind you, it's a little more complicated than this, because the other thing is that as you go to higher and higher power, it turns out the game is all about thermal management. It's about getting the heat out. And so all the units that you see, fibers are not that big, and mostly it's blocks of copper and things like that just to get the heat out. We just use fan-cooled systems because we want to, all our units are plug in the wall and go, and so it's really just about cooling of the system. So thermal management is really the key thing to scaling the power further.
Is there
Yes.
any intrinsic limitation to running them in the hundreds of megahertz to gigabit?
Well, the problem is it's hard to get the peak powers that you want once you start running so fast. So you're better off trying to temporarily multiplexing them to higher rep rates. If you go to those high rep rates, you're not going to, for a typical amplifier, you're not going to get the peak powers you need, because you're talking about getting kilowatt peak powers, and at the same time, if you want to be that high rep rate, you're going to be having pretty large amplifiers, basically. So you're better off just temporarily multiplexing by taking delay lines, putting them together if you want burst impulses that are at that high rep rate, I think.
But for biomedical applications, you may not need the super high peak powers.
Well, we need the high peak power to get the super continuum, and then you can scale it down all you want. But I need the peak power to get to, we're talking in the tens of kilowatt, 10 kilowatt kind of range to get the super continuum. Typically, we're between 3 and 20 kilowatts peak power to get the super continuum generation that we want. So one of the key things is this is a platform. So what I've just described to you works over wide ranges of wavelengths. Again, you pick your laser diode. We pretty much keep the front end the same just because we're lazy, and once we figured out how to do it, why bother changing it? It's just sheer laziness. You could change it, but why bother? The key things are, okay, you tell me what wavelength range you want. I then pick the power amplifier that's appropriate. So in particular, there's 3 choices. Ytterbium fiber around about 1060 nanometers, erbium ytterbium around 1550, or thulium around 2000. So you tell me which wavelength range you're interested in. I pick the appropriate amplifier system. Again, these are mature in the sense that not only are the fibers mature, but the pump lasers are also mature. And then in terms of the fiber that you use for the supercontinuum, well, that depends on the wavelength range that you want. So for example, if you want mid-infrared, typically 2.5 microns or beyond, you have to use mid-infrared fibers such as fluoride fibers, chalcogenide fibers, etc. If you're out to just the SWIR, shortwave infrared, out to 2.5 microns or so, from 0.8 to 2.5 microns, you just fuse silica fiber, i.e. the kind of fiber that's in your telephone network. The beauty of fuse silica, splice and go. It's got high damage threshold. It's not affected by the environment. Obviously, it's used in the ground for your telephone network. It works great. So we love out to 2.5 microns with that. If you want to go into the visible, you have to use what are called photonic crystal fibers. So for example, in the Phanium laser or the NKT lasers that are sold commercially, they're designed to be more in the visible. They use photonic crystal fibers. Or you could use some combination of those. All of these, everything here, our design philosophy and all of this is use commercial off-the-shelf parts. And we usually want to have at least 2 or 3 vendors because we don't want to be at the mercy at one company that folds and suddenly you can't make that product anymore. Very, very simple design. Because it's so simple, everyone can buy the parts, and that's why we patent protect everything. Because everyone can buy the parts, what's to keep anyone from doing it? It's our patents, basically. But again, everything is commercial off the shelf. One of the key things about this is, especially at the high power units, if you look, and again, one of the advantages of the COTS is, at the high power units, half the cost is from the pump laser diodes. And To give you an idea of, so this is a small market, even the biomedical is not a terribly large market. So back when I did Xterra Communications in 2000, we got half a watt laser for $1,000 in quantity one. I thought that was amazing. By 2006, when we started building the units, we got 6 watt lasers for $1,000. I thought that was amazing. By 2008, it was 10 watts for $1,000. By 2010, it was 30 watts for $1,000. Now it's about 50 to 60 watts for $1,000. Because there's other applications like telecom, material processing that are driving the price of these things. And so you can sit back there and for the same price, your performance keeps on going up and up because you're just leveraging the telecom technologies. So again, very simple design. It's called a MOPA, Master Oscillator, Power Amplifier, DFB followed by amplifiers, rather than a mode-lock laser. It's all fiber, no moving parts. Especially if you're below 2.5 microns, everything's placed. It's literally a strand of glass with some fiber pigtail laser diodes attached to it and some relatively simple electronics. If you go to the mid-infrared, you have to what's called butt couple or joint couple the fibers because you can't, the mid-infrared fibers are softer glass so they can't be spliced very well at least. And again, our philosophy is off-the-shelf parts because we want reliability. And what all that leads to is really cost-effective because the prices are coming down from all these other applications that are driving the technology. I won't go into too much detail, but this is just an eye chart about some of the other lasers that are out there. The key point about the OmniSciences/U of M design is number one, we are amongst the highest power up to 64 watts, but also our wavelength range is amongst the broadest out there. We could potentially go down to 0.4 microns. Again, we don't tend to do that just because there are commercial units available in the visible. We go out to, right now about 4.5 microns. The next gen will be out to 5.5 microns, and then we have a new contract that will actually hopefully get us out to 13.5 microns. Not nearly the power levels, but we're talking about getting out to 13.5 microns where a lot of the molecules have signatures out there. Let me give you an example of some of the units we built. Again, if you have questions, don't hesitate to stop me. These are, just a snapshot of some of the units. So all of these things plug into the wall. The other thing is you'll notice every one of them has a key because they're turnkey lasers, so you gotta have a key. And then one of the military requirements is you gotta have a red button. So if all else fails, hit the button and it turns off. And so there's a couple of design criteria that we use in all of this. Give you an idea of some of these. This is a 2U rack unit. So this is a 3-inch by 18-inch by, was it 19 or 21 inch deep, standard rack unit. This is a 12 by 12 by 8 inch unit. This is a 8.5 by 11 by 2 inches tall. It weighs about 6 pounds. This one is just all cooled because it's mostly just cooling, but this is 2 feet by 2 feet by 5 inches tall. And so again, getting some idea of it, let me give you a little more details on different units. This is the first unit we built back in 2000, it started in 2006, but was built in 2008. Again, it's a 2U rack unit. This is the spectrum coming out. So a couple of key things, again, you'll notice it's a continuous spectrum. So all of the spectrum's coming out simultaneously at the end of a single mode fiber. The other thing is you'll notice that it's actually a relatively smooth spectrum. And the reason for that is each pulse, if you like, has this, if you remember, there's these coma pulses, and each of those pulses have a slightly different spectrum. So what you're really seeing when you put it through the spectrometer is an ensemble average of those, which leads to a fairly smooth spectrum. So if you're replacing a lamp, that's fine. You're going to see an ensemble average anyway. Here, for example, this unit goes from about 0.8 microns out to about 4 microns with about 2.5 watts. This was originally built to replace Piplin-based OPOs, as an example, which go out to about roughly 4 microns. This was used in lab tests at Fort Monmouth, New Jersey. And when we first went in there, they plugged it into the wall, turned the switch, and it turns on. And then finally, these guys were so pleased. So finally I asked, why are you so pleased? He says, shoot, we can turn this off and go to lunch, come back, turn the switch on. And then he takes me around the shelf to the other side where they have this big BAE laser that's this big with a water cooler that you have to turn on 2 hours before you start so it stabilizes. So suddenly having this fiber unit, you turn the switch and it turns on was a pretty remarkable thing. This is a unit that's at Aberdeen Labs, U.S. Army Aberdeen Lab. This one they wanted to go from, so this one, the first one uses erbium-ytterbium fiber. as the gain medium. That's why it's centered around 1550 nanometers. So again, you tell us what you want. We select the parts based on that. This one, they wanted to do 2 microns out to 4.5 microns. This is used for infrared countermeasures. This is where the heat signature, in other words, the way that smart missiles find aircraft or vehicles is by the heat of the engine. And the heat of the engine, particularly for a helicopter or an airplane, is roughly from 2 to 5.5 microns. And so this is sought to emulate the heat of the engine, basically. So here we start instead with thulium, because again, we needed to go starting from 2 microns, and we go out to about 4.5 microns. To give you an idea, this is some residual, again, we don't evacuate the spectrometer, so there's some residual water absorption here. And again, this is the CO2 line. This dip you see here is the CO2 line. So we're actually going to the other side of the CO2 line with this spectrum. Yes?
So each 280 pulse has this.
Say again?
So each pulse that comes out, this one is like.
Each 2 nanosecond, 2 nanosecond pulse has this spectrum, but within each of those pulses, go back. Sorry. Here. Each of those, so let's say this is a half nanosecond pulse. So each of these half nanosecond pulses has that spectrum, but that half nanosecond pulse has these fine structure pulses underneath it, each of which has a slightly different spectrum, which ensemble averages to give that spectrum. Does that make sense? So each of these pulses have a slightly different spectrum, but when you take the ensemble average over that half nanosecond, you get that smooth spectrum.
How stable sort of pulse?
Ah, okay. Glad you asked. Go through the numbers. We have actually more stability test as well, sorry. Get back to where I was. We do have the numbers on some of those, to give you an idea. As in a quick snapshot, and go unit by unit, this is plus minus 2%, plus minus 0.1%, plus minus 0.2%, plus minus 1.35%. A quick snapshot. This is, again, this is the first unit. The second unit we built here, I think, again, the specs were plus minus 5%. I think we did better than plus minus 2% or so. Again, all of this, again, coming out of a single spatial mode beam. So this is being used in, again, experiments at Aberdeen. This unit is at Wright-Patterson Air Force Base. This was used in some field tests, and they now have it. The M had to come off of this because it turns out the football department owns the logo. So you can't use M liberally, so we had to take the M off of it. So omniscience I control, but M I don't. Anyway, no, so this gives it, this was urban ytterbium, and again generated spectrum from roughly 1500 to 2500. So we used a lot of the SWIR experiments we do using this. Again, power stability about plus minus 0.5% or so. You might ask where the stability comes from. Mostly what you'll see is over the passage of time, again, because our philosophy is COTS parts, commercial off-the-shelf parts, by the time we got to this unit, half the parts were available, polarization maintaining, half weren't. And so actually the second half of I think it was part of the way polarization maintaining and part of the way non-polarization maintaining. So most of the fluctuations come with environmental changes, the polarization rotating, changing. By the time we got to the next 2 units, this is an example of a 25 watt unit and then a 64 watt unit. Now we're all polarization maintaining. And so our stabilities have actually gotten better over time, not because we did anything significantly different, but because all the parts are now available in polarization maintaining fashion. And so that's really where we think the stability has come back. This is a 25 watt unit. Turns out this was a bench top. They didn't pay for us to package it. So this is classic of what we do at the university. We build a bench top unit, prove the concept, show the parts, and then we say to customer, if you want to have a box built, Omni will build the box for you. Customer in this case didn't want to pay for a box, but they had the demo unit. This put out 25 watts. Again, you can see the military always wants to go higher and higher in power. This put out 25 watts between about 2 to 2.5 microns. So this is, sort of SWIR band 2, if you like, from 2 to 2.5 microns. They wanted to look at the combinational bands for a lot of the targets of interest for them using this laser. And so, again, as we go up in power, we've now, in many cases, added an additional stage of amplifier so that each stage itself doesn't have to generate too much power, and so more stages of amplification. Just to illustrate the point on some of the features on this, we talked about that you can power scale this with repetition rate. So here's where we vary the repetition rate, megahertz, and we look at the output power. You can see it scales linearly, and as long as you adjust it so the peak power is the same, the spectrum scales as well. So in that sense, it's a power scalable laser. The other thing is we verified the beam quality, that as we varied the power, that we can see m squared is still in the range of pretty, within sort of experimental error. It's transfer limited beam coming out. And the other things in terms of the fluctuations for this laser, this is looking again at the fluctuation different power levels. At all the power levels, it's less than 0.6% variability. And so the key point is that yes, it truly is a power scalable laser by adjusting the repetition rate of the pulse, so long again as you maintain the peak power to be the same as well. The unit that's actually one that so we don't actually own any of those other units because the government customers have taken them, they paid for it, they get it. This one we said, you're paying us so little money, you don't get to keep it, we get to keep it. And so we actually have this in our lab, and actually the one, Bruce, that we're proposing to potentially bring down here if there are some experiments that are in fact worth doing. This is a big unit. Again, if you took off the top of it, you'd see just cooling. It's just all cooling in there basically, because fibers don't take this much volume. It's really just big copper plates. You can engineer it much smaller, obviously, with thermal management. We don't do thermal management because again, most of our government customers pay us to prove efficacy that you can do this and it works in the experiments. This unit, again, is 2 feet by 2 feet by 5 inches. We originally had it in pine like a casket, and the government customer complained about that, so we then went out and got some cherry stained. Didn't look too cheap at pine, I guess. So again, our classic, we got let's see, there's a switch there, so it's a turnkey laser. And then, of course, if all else fails, hit the red button. And the particular details of this are now we're starting with the ytterbium because this was required to start at 1 micron, go up to 1.8 microns. So we're starting with the ytterbium, and we're starting a DFB at 1060 nanometers and using what are called ytterbium fibers. Pretty much now we use double-clad fibers all the way through just because the pumps are much easier to do with that. And then at the output, we just again have a length of fiber, I think about 8 meters or so. The beauty of, by the time we got to this laser, which we built last year, started a year and a half ago and built in about 6 months and made it last year, that now all the parts are available polarization maintaining, and so actually the polarization state is pretty well fixed. And if you want double the power, you can polarization multiplex 2 of these units together, presumably. This is what the output looks like, so take a little bit of time to explain what's going on. This is the spectral density in milliwatts per nanometer. And so you can see going up to 500 milliwatts per nanometer at the top range here. This is the spectrum. And so this is where we start off the pump at 1064 nanometers, ytterbium. And then this is the supercontinuum generation. There's a whole bunch of physics behind the features here I won't go into because of the time constraints, but the key point is that now you have a supercontinuum that goes all the way from roughly 1060 nanometers out to 1800 nanometers, output power of 64 watts. The peak powers are about 18 kilowatts or so. The next gen of this, we already have a contract, or they're writing a contract, we haven't seen the money yet, but that will go out to 2.5 microns. So it'll be at least a 50 watt unit going out from 1 micron to 2.5 microns on this same basic kind of architecture. Some of the features of that, so you've asked again of power stability. You'll notice now that we've gone all polarization maintaining, so if you look on a long hour time scale, this is the kind of output you see, and if you actually blow it up, you see the power stability is about plus minus 0.2%. Again, as you vary the rep rate, you can see that the power scales up as well. And one of the key things, so this was what the original military targets were, and this is what we achieved. One of the things I want to point out is that the wall plug efficiency. Every quantum cascade laser maker lies to their teeth about this. Most laser makers also do, by the way. But our wall plug efficiency, we buy from Amazon or whatever what's it called? There's a unit you put on your wall plug and it's called kilowatt, literally what it's called. We measure how much power is coming out of the wall. and we measure with the power meter what's coming out of the laser. And what comes out of the laser divided by what's coming out of the wall. This is true wall plug efficiency of close to 16% for this unit. So it's very efficient. We also have in case you want to do eye safe only, so-called eye safe, we have a filter in there. You can block the light before 1.4 microns. That's, again, depends on the safety issues and the experiments that you're doing here. This is a unit that we have in our lab right now. It's gone through 3 field tests. Let me talk just briefly about some of the field tests. I won't, as I said, I don't want to spend a lot of time on this because you're not the military customer, or, but what most of these field tests involve, for the last, we've had 3 unclassified field test at Wright-Patterson Air Force Base, and then a 4th classified one at AP Hill in Virginia, which I can't talk about. But typically what happens is we have the laser in a 12-story tower, aim it at a target a mile away, and then on that target, which is a 8-foot by 8-foot board, various samples of interest are placed. There are spectrometers, FLIR cameras, hyperspectral imaging cameras on the ground, and then they're taken up to the tower. So for 5-watt units, all the diagnostics are on the ground because there's not enough power for the diffuse reflection to come back to the tower. At 64 watts, all the diagnostics are actually right next to the laser up in the tower. And so you can get enough diffuse reflection back to the tower. One key point is you tell them, no one believes you. You know, the light's coming out of single mode fiber. What else can it be other than nearly transform limited? We don't believe you because we got to go a whole mile. So this is when you go through a mile through the atmosphere, you go to the bottom. This is what the spectrum, the spatial mode looks like. It's m squared of 1.22, which is close to theoretical minimum because m squared of 1 is actually a Hermite-Gaussian, but the fiber mode is a Bessel function. And so m squared of 1.22 is actually pretty close to theoretical minimum. What does it mean to you? For the guys in the military, it means even after I go 1 mile, I've got less than a meter, or half a meter diameter beam. For you guys, it means you can focus this as tightly as you want, basically. And then we've done spectroscopy with it. Again, I won't go through a lot of the details on that, but let me kind of summarize the military results. Again, a lot of experiments have been done, but we've shown that we can propagate the beam through a mile or 1.6 kilometers. Spectroscopy of the samples using that laser, beam quality m squared less than 1.3 throughout the range. Although there is a lot of variation, but that comes not from the laser, but from the turbulence. And with the 64-watt unit, we're now at the same illumination as the sunlight illumination. So currently these hyperspectral imaging cameras or systems use sunlight as the illuminator. The problem is they only work from 9 to 3 on a sunny day. But now with this kind of laser, it can basically be an active illuminator allowing for 24/7 surveillance, which is the reason that the lasers have been built for that. But again, we've used that, as I said, the laser I just showed you has been used in 3 field tests thus far, and the next gen is being built based on the results of those field tests as well. So we think that, as you look at that spectrum, we've talked with a bunch of you about, talk to you, back to the spectrum. But, whether you're doing, this morning we're talking with the OCT folks, and I apologize, I won't remember everyone's name, but, you could potentially, for example, do OCT between 1.1 and 1.3 microns, getting you 1 micron type resolution, while at the same time doing dual modality of measuring the chemical composition of the tissue of interest, whether it be collagen, elastin, what have you, and going to breast cancer, which is kind of where our discussions began. We get nice light around 1200, which gives you certainly the second overtone of collagen and adipose and lipids. And then as you go to 1450, you've got a waterline. And then as you go to 1700, you've got the first overtone for lipids and collagen as well. So again, you've got a range of spectra that you can examine using this as you get into the power ranges. And I think I read in some of your papers that, well, we don't use supercontinuum because the light intensity is too low and the cost is too high. We might be able to figure out how to solve that problem because we are at a much higher power. Yeah, well, and I think we would, if it were commercial, we would be much more cost-effective compared to the other, because we're not starting with a mode-lock laser. If you look at it, their cost is really coming up because of mode-lock laser, photonic crystal fiber. We're not using photonic crystal fiber. We're not using mode-lock lasers. It's really a much simpler design. However, nothing's for free. So there are differences of the applications that you need to use it for. But again, we're very interested in collaborating. What we do with the med school, honestly, I go in and I say, how crazy is this idea? And yeah, okay, so 9 out of 10 times they'll throw me out of the room and say, that is crazy. But then, there's occasionally that crazy guy who'll say, that's not that crazy. Maybe we should try it. And so we work with the guys in FNIRS. They say, well, that doesn't sound that crazy. Let's try it. And we work with the guys in cardiovascular medicine who are a bit of on the crazy side, but they say, yeah, let's try different things. And so we are very interested in finding new applications because we have a hammer and we want everything to look like a nail. And so biomedical for us looks like a nail out there. Sorry, there's a lot of data. I'm not sure how much this recording thing is actually slowing down my computer. It's working a lot slower than it normally does, so who knows. Let me give you 2 applications that we're working at. I'm sorry, I hope we don't run out of time. I'm just going to give you a flavor of the kind of experiment. These are now ongoing experiments. We've done a lot of experiments in dermatology with Jeff Warringer, who heads the laser cosmetic surgery department. So we haven't looked at burns, but we've looked at acne treatment. We've looked at skin tightening by shrinkage of collagen, things like that. We've done a lot of work on renal denervation for treating hypertension by hitting the arteries and they go to the kidney and whatnot. But I'll give you 2 ongoing experiments in our lab, one on the diagnostic side and one on the therapeutic side. Again, I bring these up partly because I think it might be relevant to some of the things we might think about doing together. So first experiment on diagnostics is non-invasive glucose monitoring. I don't have to remind you how big a market it is and how big a problem it is. Basically, the only accepted way of measuring glucose level is by pricking your fingers right now. So, on the military side, we look for hydrocarbons because camouflage nets are made out of plastic, which are hydrocarbons. But then on the medical side, well, there's a lot of hydrocarbons in you. In particular, glucose is C6H12O6. That has all the usual suspect bonds in it. So if you look at the spectroscopy of it, certainly the fundamental lines are in the 4 to 10 microns, but you just don't have a chance in hell at seeing those because it's all blocked by water. You're lucky to go through 100 microns at best. And so, just can't see those. So yeah, they're very strong, but you just can't get to them. The flip side of the coin is if you go to the second overtones and higher order combination, much of the work that you guys, for example, work in, we don't work in because 15% of your blood is hemoglobin. And I'm looking for, remember, in a typical non-diabetic, probably a little bit different after you eat pizza, but a typical non-diabetic, you have a teaspoon of glucose in your entire body. So you're never going to see glucose through hemoglobin. And so we purposely stay beyond 1.2 microns so that we're avoiding hemoglobin. And so that naturally leads us into looking at 2 wavelength windows, the nonlinear, or the combinational bands between 2 to 2.5 microns, and the first overtone bands, the 1.5 to 1.8 microns. In particular, this is FTIR spectra. The blue curve is glucose. And the other thing, again, you guys know this, but point this out, if you look at water overlaid with it, the key point here is, again, you can't see through water. There's just water everywhere, right? So there's a peak at 1450, which is back here. And then there's a big peak at 1950, which is blocked out here just because you just see noise because of the water background. And of course, it starts climbing after about 2,400 nanometers, going up to 3,000 nanometers, where the water just supersedes everything kind of thing. But in these 2 water valleys, there are 5 discrete signatures for glucose. These are the overtone bands around 1587, 1750, and these are the combinational bands 2120, 2270, 2320. And so the 800-pound gorilla in non-invasive glucose monitoring is how to see these lines. And all of those studies have used tungsten or halogen lamps to do them. And they've looked through thick parts of the skin. Almost all the experiments are done in the forearm, which has very thick skin. And the end result of that, after hundreds of millions of dollars being spent on it, number 1, they've actually made it through clinical trials, phase 1 and phase 2, and have all failed in phase 3 because they just barely had enough SNR, signal to noise ratio, to get a reading. But then as soon as you remove the constraints of placing it precisely and whatnot, there just isn't enough margin. And so the name of the game for us is signal-to-noise ratio, or margin. How do we get signal-to-noise ratio? And that's really where our light source comes in, along with some other schemes. So the other thing is that if you look at all the studies, even though people talk about having studied all this stuff, it turns out almost all of the data is around this one line. And you may ask why? Well, if you look at the constituents of skin, because again, by definition, non-invasive glucose monitoring means you're looking through the skin. So your skin has adipose, collagen, elastin, and of course water. And those are the various spectra that I've overlaid here. And again, you guys will recognize this obviously in your 1210. You see the adipose and collagen lines. Again, the next one, the first overtone's around 1750 or so. The red again is collagen, the black is adipose. You won't see these lines because they're going to be masked by water, basically. 1450 dominates it. But the point is now if I overlay the glucose lines, what you see is you cannot see the forest through the tree on most of these lines. The only one that has sort of the opposite behavior is the 1587 line. And so almost all of the work that's been done basically has been by looking at that one line through the skin. So there's a couple of problems. The number one problem is avoiding hemoglobin, work beyond 1200 nanometers. Number two problem is minimize water. You can't avoid water, minimize water, so work on the valleys of water. And number three is how do you get through the skin? And so our answer on that is pick, first of all, the thinnest layer of skin. We believe that behind the ear is where you have the thinnest skin. That's where the epidermis, for example, is less than 50 microns thick. People who do ear surgery know that. That's why they always come in through the back of the ear. It's not exposed to trauma, so there's no reason to necessarily have a thick skin there. The other thing is that you get offshoots from the carotid artery, which feeding the heart to the brain, so it's the best blood representative glucose level, and so you've got a good blood flow there. And then the other thing is you've already got watches and things like that measure the heart rate. Let's synchronize to the heart rate because the skin doesn't change at 60 or 70 times a minute, but the blood flow will. And so by synchronizing, using lock-in techniques around the heart rate now, we preferentially look at the blood flow as opposed to the skin by doing this. So our playbook on this is a book by John Smith. He used to be head of the glucose monitoring at Johnson & Johnson. He has a book called The Pursuit of Non-Invasive Glucose, Hunting the Deceitful Turkey. It's named after a story by Tom Sawyer where, as a boy, he would try to catch this turkey, and every time he would walk up to the turkey, wouldn't budge, and then as soon as he's about to leap at the turkey, he goes escaping off, and all day he spends trying to chase this turkey. Well, it turns out that people always show these Clark graphs, and it turns out that almost everything under the sun will correlate with the Clark graph. And so what he says in there, the single little appreciated law has by itself resulted in inappropriate spending of hundreds of millions of investor dollars in the area of non-invasive glucose region. And what he recommends actually instead is that you use what's called a test of technologies. And here's his recipe, and this is what we're working on. Test one showed that you can, in a laboratory, measure 1 milligram per deciliter of glucose in water. Let me explain the rationale behind that. So average non-diabetic has about 100 milligrams per deciliter. Ranges from 70 to 130 depending on whether you're just waking up or right after a meal. So, and a commercial glucose meter has to measure 20 milligrams per deciliter. So if you can't, in a laboratory, in water, all this control setting measure 1/20th of the eventual resolution you're going to need, you don't stand a chance of a prayer of measuring it eventually in the commercial system on a human. Step one. We've actually gone through that. I'll show you some of the data on that. Working on step two now is now create artificial blood, this turbid liquid medium, if you like a phantom blood, or you can measure 5 milligrams per deciliter. Again, the idea is that even in the phantom blood, in a laboratory setting, if you cannot measure 1/4 of the resolution you're going to eventually need, you don't stand a chance in hell. And oh, by the way, everything is dominated by water, and water's spectra changes with temperature and humidity, and so show that with changes in temperature and humidity, you can still measure these things. And so I'll show you the results in test one. We're working currently on test two. So in test one, we used one of the light sources I showed you earlier from 1550 to 2400 nanometers. I won't go into details, but we use a dual arm setup, basically differential. So in one arm, we have a known sample, i.e. water, and then the other, we have the glucose sample under test. This is what the typical spectra look like. This is looking from a range from 100 milligram per deciliter down to 5 milligram per deciliter. A couple of things you'll see here. One is just because over the course of time, temperature changes and the water line changes, you can see already the tail coming up here. The other thing is you can start to see some interferences from what are called Fabry-Pro effects. These, we believe, are coming from the cover on glass on the detector itself. And part of that reason it comes up is because we're looking at the 4th decimal place. So these are fairly accurate measurements, and so all these little things actually start to come in to play. Perhaps most convincing, if we look at this line here, for example, and this line, is as a function of concentration. This is showing from 100 milligram deciliter down to 25 milligram per deciliter for the first line here, this 2120 line. You can see that it's linear with concentration. And as I lower the concentration further, this is showing from, I'm sorry, I skipped over one slide, I think. This is going 2120. This is the second one, 2280. Line, again, you can see linear with concentration. If I go down to the lower concentrations, this is again from 25 milligram per deciliter down to 1. You can see we continue to be linear down to 1 milligram per deciliter. And again, likewise for the second peak, down to 1 milligram per deciliter. So we've talked to a lot of folks, everyone from Apple to Microsoft to Dell to Johnson & Johnson. The folks at Johnson & Johnson have said there is no other non-invasive technique that's been able to get down to 1 milligram per deciliter. The only way people have gotten down to 1 milligram per deciliter is by extracting blood and mixing chemicals in it. And so this is, to our knowledge, and to everyone we've talked to, the only non-invasive technique that's actually been able to get down to 1 milligram per deciliter.
Are you still at the spectrometer end, or are you using FTIR techniques?
We're using spectrometer right now. And again,
Graded-based?
we're using grading-based. We have a laboratory one right now. We're talking to Texas Instruments about getting their DLP-based ones, it's a compact spectrometer. So yeah, that's what we're doing now. We aren't using FTIR at this stage. One of the reasons is because we're pulsed, you got to worry about, you got to appropriately adjust the electronics of the FTIR to take into account the pulse. So our holy grail here, so it's both a problem as well as a potential application. Our holy grail is that you go into a doctor's office, you know, they put a thermometer in your mouth, they know your temperature right away, they put a blood pressure machine on you and measures your blood pressure, and that maybe we could do a quick scan of your blood just to see if it's worth, you know, there's something to be concerned about. And the point is that obviously there's glucose, but there's a lot of other things that have signatures in this wavelength range. And so if you could do a quick blood scan, you know, depending on what you're worried about for different constituents of blood, perhaps you could then do just a preliminary blood scan using techniques of this sort. And that would be something that, while the doctor's there, is done while you're sitting in the office. Yes?
So these graphs that are based on physiological concentrations of the compounds in the blood?
No, these aren't necessarily representative levels. We are working on more representative levels, but these aren't necessarily representative. These are what they say they are, but they aren't necessarily representative of what it is in the blood, if that's what your question.
Basically, can you measure glucose in the presence of all these things?
Well, yes, that's what we leverage from the hyperspectral imaging camp. That's because that's exactly the same problem hyperspectral imaging. How do you see, target A amongst the others? And so we're using the machine learning algorithms basically from hyperspectral imaging over into the blood constituents. But my point is, once you've got the library built up, not only can you find the chemical of interest potentially, but we can, for example, look at triglycerides, cholesterol, ketones, and other things, each of which have a distinct unique signature in that wavelength range. And there are different varieties of hydrocarbon bonds. And so again, the holy grail is, could I go in and do a blood analysis pretty quickly? Not the gold standard of being the replacement for the blood test, but something, just a quick scan while you're sitting in the doctor's office to...
But that whole back-end analysis is what a lot of the money has been invested in over years.
That's right, but we just want to take it and use it.
So is the sort of the key advantage that you're going to have just better signal to noise?
So what I'm told by the HSI machine learning guys is, with this spectrum, this kind of overlapping spectrum, two things are key. Number one, having as much of the spectrum as possible. The more information, the better. And number two, an SNR. Mark Arnold at University of Iowa estimates that you need an SNR of 50,000 to 1 to be able to reliably measure these.
So that's killing all those sort of
Yeah. So we've done the numbers, Bruce, and our estimates on improvement, potential improvement in SNR. I don't think I have that chart in here, but from the light source, we get about a 77-fold improvement over a tungsten lamp. So, almost 2 orders of magnitude. By working behind the ear, we get another factor of 15 or so. By using locking techniques, about a factor of 18. And by using 5 lines instead of 1, 5-fold improvement in SNR. And if you were to get all of these, big if I were to achieve all of those, I would have 10 to the 5th improvement in SNR compared to what's done today, or has been done by various companies. Now again, I'm not going to get the 5 orders of magnitude, but the point is I've got headroom where even if I get 1 order of magnitude, I'm starting to get into the beat the margins, and I've got more space to go, kind of thing. So as all engineers, any rule of thumb, if you don't even have an order of magnitude pocket, don't start, because by the time you get there, it'll be a factor of 2, and all the way the technology's moved. And so with 5 orders of magnitude in your pocket, even if I can start to eat at it, I stand a chance in hell of doing the measurement. But again, glucose is obviously one that has a huge market people care a lot about. But at the same time, boy, if I could do blood, imagine if I could sit in a doctor's office while those 3 minutes the doctor's going to spend with you, the nurse or the whoever gives him the chart of here's what any things they need to worry about, just a quick screen. That would really be one of the things that people would care about. But we are. Again, we're going back to the root. This is all paid for by the government for hyperspectral imaging. And this is, instead of looking from a drone down at the ground at military targets of interest like bombs and camouflage and this is the same technology on the skin, use the same kind of algorithms and everything with the different libraries, basically. So you're going to instead put in these different libraries rather than the library for, explosives and things of that sort. Yes? Well, when you scream, I stop. So one thing is you can put, obviously you probably are going to be less than 100 milliwatts, but if you want to go beyond that, you have to do cooling. So all the derm experiments cool the skin. So whether they do nitrogen cooling or whether they put a water flow around it. So if you want to exceed that, you've got to put water cooling. So, or some kind of cooling in addition. But if you look at dermatology, if you turn a derm laser on, you're going to get a blister unless you put on the cooling at the same time. So again, hopefully you don't need that much power. And the other thing is that you can try to beat it by first filtering and then hit the skin, as opposed to put the whole spectrum on and then filter it. So, put your spectrometer advanced. It's a linear system, so you could put the filter on either side, kind of thing. So that's one of the things we're working on. I'll give you another example. I'm sorry, I've run out of, do we have a few minutes? Or? Okay. Yeah, I really have run out of time, but I'm going to go one more. Oh, you want to get rid of fat? Yeah, right after lunch. Well, all right. So this is sort of and I wanted to point this out because when you get to, so broadband is great for diagnostics, but when you want to instead do therapeutics, you want to have all that light at one wavelength. So you don't necessarily want to use a supercontinuum laser. So you use your supercontinuum laser to figure out what were the right wavelengths, but then do a different kind of laser to hit that. So what we're working on in particular is there are a lot of, I should say, hypotheses, not convincingly proven, but there are a lot of hypotheses that obesity is, well, it's well known that obesity is associated with type 2 diabetes, but the hypothesis is that visceral fat builds up around the abdominal organs and the heart, and this leads to insulin resistance. So, mind you, there's always a certain amount of fat, right? Because if you don't have the fat around these organs, every time you walk, your organs are going to jiggle all over the place. So you need to have a certain amount of fat. But as you eat pizza, go to McDonald's, eat out too much fast food, you get too much of that fat and the visceral fat. Again, let me distinguish that from the subcutaneous fat. Subcutaneous fat has no correlation to type 2 diabetes. However, the visceral fat is believed to be related to the insulin resistance. And so there have been animal studies done where they've proven that by removing visceral fat, that the insulin resistance can reverse type 2 diabetes. But the problem is that people are afraid to go in there because your vital organs are in the abdominal region. And so when trying to remove the fat, you may cause more harm than good. And so the notion would be down the road that one would look at a laparoscopic type procedure where you go in laparoscopically and you melt that fat and suck it out in some fashion. But very importantly, you need to have some selectivity because you don't want to damage the organs around it. And this is one of the key things, that we need to have some sort of selectivity. Now, why that's key is because almost all commercial medical lasers are based on heating water. And so most lasers operate by heating water, and in fact, adipose, if anything, is the other way around. It has very little, if no water. And so actually, if you use the commercial lasers, what they would do is heat the tissue around it and transfer the heat to the adipose, which would more likely cause damage to your vital organs. So instead, we want to selectively hit the adipose while minimally hitting water. We can't avoid hitting water, but we want to minimally hit the water. And so that naturally leads to you to working around either 1210 nanometers or 1720 nanometers, two wavelength windows where the adipose absorption exceeds the water absorption. Again, mind you, you can't get rid of water absorption, but at least you're operating at wavelengths where your adipose is stronger than the water lines. And by the way, if you want to do spectroscopically, you can again see adipose or lipid and water sort of in this whole wavelength range, basically. Incidentally, we talked a lot with folks this morning about collagen of interest as well. So collagen, incidentally, also has lines around that wavelength range. So likewise, if you're doing, for example, you want to hit collagen, you can also hit those in that wavelength range. So now, instead of supercontinuum, we want all the light in one wavelength. And if we want to do that, well, we started off back in 2010 or so, building what are called cascaded Raman oscillators. What you can do is you can basically start off with your pump wavelength at one of these amplifier wavelengths that are well established, and then hop your light to the wavelength of interest. Well, you can do that, but and so when you did it in the laboratory test or laboratory setting, and it took a half a laptop bench. But we've actually sort of retired all of those because along come laser diodes that come with higher power. So today, I should say, these are 3-year-old laser diodes at this point, so the technology's probably moved another gen since then. 980 diodes, this is sort of our gold standard. They were 30 watts back then, now they're about 60 watts, unit about 1 inch by ½ inch or so. I'm not showing the cooling and all that goes with it, but again, this is just a laser diode head. 1210, again, that's what the unit looked like on the benchtop with cascaded Raman, but again, you can now get 12 watt units. This was as of 3 years ago with at 1210, and at 1700, a little bit tougher there, but around 7 watts and 1700 nanometers. So, and we've also measured these different laser diodes to see how far the penetration depth and damage is. So for example, at 980, we get about a 5 millimeter damage depth. At 1210, about a 3 millimeter or so, and about less than 2 millimeters at around 1700 nanometers. So one of the things I told you was selectivity and also concern about the fat that grows around the heart. So this particular one, we used a sheep heart, and sort of the whitish things that you see here are the fat that grows on the heart. I want to just illustrate to show you sort of the selectivity a bit. See if this actually works. So this is a video of a procedure this is in vitro. That's the sheep heart. You'll see the laser coming on somewhere. You can see the laser's been put on, just sort of running it across. And so the whitish area is the fat on top of the sheep's heart. And the key point is you can see the fat is melting, but you're not seeing a browning or burning of the tissue below it because of the selectivity. Again, this is being done at a wavelength where we're melting, or we're tuned into the adipose line. Obviously, you've got to suck this out or something. You can't have this sitting, you don't want to have that sitting in your abdominal region. But again, if this were a wavelength that were hitting water, it would selectively first heat the tissue and then transfer the heat to the adipose. Instead here, we're melting the adipose without significantly damaging the tissue. To actually prove that, we actually did histology on some of these samples as well. And when we did the histology, This is looking at, so this is sort of a cross-section the other way, meaning here's the heart tissue, here's the heart tissue, and then here's the fat on top. And when you sort of do a sort of slice down on it, what you see is we get a small damage region on the myocardium, which it may actually be just from cutting of the sample, but then a 0.5 millimeter pericardial damage region. Again, important for the selectivity part. So the experiments we're doing now are in rat models. We're using the 1210 diode in particular. And then we focus the light with this. You'll see a black probe in these things. We're working with Randy Seeley over in surgery, where he's got rat models of various sorts. Again, our goal is to hit the visceral adipose tissue fat, and in particular, the hypotheses of the pockets of interest are the pararenal fat and the epididymal fat. Regions which are believed to be related to type 2 diabetes. We're still, just beginning this process, but here in the example of the rats, in the case here of the pararenal fat, there's the kidney, for example, and the pararenal fat around that. Here's the testes, and here's the epididymal fat around it, just to illustrate. So this is just a video of the small fraction of the procedure that's being conducted. In this case, we're not actually melting all the fat and removing it, but we're using the laser simply to loosen up the fat or cut the bond, if you like, with the tissue, and then remove it surgically. Now, down the road, we would envision melting all this fat and sucking it out somehow as we go to a more laparoscopic type procedure. Right now, it's open surgery. But the laser, which is here, we don't have a tracer beam on it yet, but it's going in here, it's melting the fat. You can see the discoloration of the fat, and then we can remove the fat after it's been the bonds have been melted off, basically, using the laser. Again, you don't have a tracer beam here, so you can't see that. Likewise, that was the epididymal fat. Here, just another example with the pararenal fat. Again, you can see the kidneys are here, and then the pararenal fat around that. Again, here we're merely using the laser to loosen up the fat to be able to remove it off. And the key point again is that we're not damaging the organs. Again, if we were the more typical medical lasers that are used, they would lead to damage of the organs before melting of the fat. By tuning into the adipose lines, we're melting the fat preferentially. Again, we can't avoid water absorption, but we at least selectively hit more of the fat than we do of the water. And you can see the fat being removed in this case, again. New laser diodes are available now that also have a tracer beam for the obvious reason you don't know where you're hitting. And so the new versions of these laser diodes actually have tracer beams in them as well, so you'll know where you're hitting. So if we ever got funding behind it, that's what we would do, would buy the new laser diodes. And the powers, of course, are coming up as well. But that gives you an example. Again, I know I'm way over on my time. Apologize for that. But let me summarize. So we have our tool bag, our fiber lasers, supercontinuum lasers, and obviously migrating toward semiconductor lasers. Our novel modulation stability supercontinuum lasers are power and wavelength scalable. We use all commercial off-the-shelf parts based on mature telecom fiber optics fields. There are no moving parts. We think down the road cost-effective, compact, and reliable lasers. We've generated supercontinuum all the way from 0.8 to 4.5 microns, covering several octaves of light, power scaled thus far up to 64 watts and be higher in the near future. We've done hyperspectral imaging with the intelligence community. And I wanted to give just some of the example of some of the experiments that are ongoing. And all of our experiments, we believe in teaming up with the light source guys. We work with, in the case of the diabetes treatments here, with the Department of Surgery, Randy Seeley and his group, and the non-invasive glucose monitoring. We work with Hitinder Gurm over in cardiovascular medicine. So we're not the medical experts, but we kind of agree on what are the right kind of experiments to do and what's the right design of laser. Honestly, the reason they gave me an appointment in med school, I think they're crazy, but is that everyone comes to them and says, I've got this laser, you should use this. And we come in with a different attitude. We say, look, let's figure out your problem, then we can design whatever laser you need. So that we build a laser to the application rather than saying, this is what I got, will you use it kind of thing. And fundamentally what's different is that almost all, it's like a microwave oven, right? Microwave ovens work on heating water. And don't put metal in the microwave oven, but any food that has water is going to sooner or later work in the microwave oven. So all of the medical lasers that are sold out there commercially are based on basically heating water. Here, because we can choose our wavelengths, we can do diagnostics over a range of wavelengths. Things that we care about are usually hydrocarbon-based because those are naturally in our sweet spot. But, we're talking about adipose/lipid, collagen, elastin, and of course water as well. But usually we try to skip around water for a lot of the applications we're doing because you're dominated by water. But for whether it be for selective ablation or for being able to diagnose whether it be breast cancer or glucose monitoring, you need to skip around the water to get to some of the other ones, although you might disagree on the water part on some of your TOIs that you have. But we really are very interested in collaborating because we have a tool, and unless people use our tool, well, we're just a tool maker. Well, thank you for your attention. Yes.
You design off-the-shelf, inexpensive off-the-shelf components for military lasers.
Right.
Does that restrict a lot of your publications?
No. So one of the things is, so everyone understands the business of ITAR, I think, and classification even worse. So yes, I have a top secret clearance, but that's more to understand the government needs. But number one, we have patented everything we do with permission of the government. And number two, we have published, except for the latest results, and I can't talk about one field test that it was actually classified, but we've published most of our stuff with our government sponsors as co-authors. Turns out that motivates them to get the paper through the process. But as a consequence, we've avoided the ITAR rule. So what's usually classified in ITAR are the samples of interest and the signatures associated with that. So we don't obviously publish things of interest to the military. You won't see any camouflage net data in our publications. So that kind of stuff is, kept separate. But that's how we've avoided the ITAR. We've patented with government permission and published everything that we've done until the latest. And again, we just haven't gotten around to finalizing the paper on it.
So in the military, these are primarily diagnostic tools?
There's two applications for the military that they've cared about. One is infrared countermeasures to basically replicate the heat of the engine signature. The reason they care about supercontinuum is right now people use OPOs to generate that at 2 wavelengths, but the military the enemy can measure those 2 wavelengths and just put an AR coating or absorber at those wavelengths and defeat the system. With the supercontinuum, you really can't defeat it because if you go to block the light, you will block the signature of the heat of the engine as well. That has kind of passed by because that was hot during the Iraq-Afghanistan wars because the helicopters were getting shot down. But after those wars have ended, they're not putting IRCM systems on drones, I guess. They have less of an interest. But the intelligence community cares very much about identifying targets based on their chemical signature. And so that's the bigger push now. And so that's why most of the work is shifted to hyperspectral imaging. But, they're not only just for overseas applications, but even within, obviously domestic terrorism, I guess, whatever the term that's used. People worried about, the guy who, big vicar driving up to the Merrill building in Oklahoma and blowing off a truck full of fertilizer and things of that sort as well. So that's become more of the area of interest right now. But the key point, though, for you guys and for us is that's great because that's exactly what you need for blood and light measurements or any of these, if you're trying to identify what the military, when they say identifying targets, they mean identifying targets based on their chemical composition. Well, that's exactly what you need in the medical application for these diagnoses. So it's really part and parcel of the same thing. But the problem is not our light source. The problem is these freaking cameras cost $300,000 to $1 million. And so it's the focal plane array problem, not the. We would argue it's not the light source problem. It's the camera guys are still outrageously priced. But I think there's a ways around it because in the government they have to. When that drone's flying overhead, they need all the information and they will not sacrifice a photon. Whereas in the medical, you can afford to have your patient sitting there for a minute maybe to do this. And so you can raster scan it and get that image instead. Other questions?
Are you pushing the source performance down to, let's say, picosecond or sub-picosecond regime?
Now, if you're going to go down there, you usually go to mode-lock lasers, and you can do that. But that would be the natural way to get down to mode-lock lasers if you want to do that. So people who want to do that way, we say start off with the mode-lock laser and generate the supercontinuum. You can do similar kind of schemes. But again, you don't get as smooth a spectra if you do that, because usually you don't have the pulse ensemble averaging and whatnot, so you'll see a much more featured supercontinuum. That's not our bailiwick. Our bailiwick is COTS and lower in cost and simple laser. So we're not looking to do time-resolved spectroscopy. For that, you should use a mode-lock laser. We'll be the first to admit it. What we're looking to do is anyone who's using a tungsten halogen lamp but needs better SNR or needs the ability to focus it onto a DMD or something like that, that's where our sweet spot is. And so, that's what we look to do, basically.
How about with new fiber materials like photonic crystal fibers or some other, fiber structures? Are you exploring some of those as well?
We are mostly looking at the longer wavelengths rather than shorter wavelengths, because most of the shorter wavelength stuff are commercial. So what we do is, for example, fused silica, I happen to have these, but fused silica goes out to around 2.5 microns. The fluoride fibers we use right now go out to about 4.5 microns. And then the new fibers coming on board, indium fluoride fibers, go out to 5.5 microns. And then even beyond that, the chalcogenides may take us out to the 13 micron range. And so because our customers, we do what we're paid to do, I suppose, but because our customers care really about the chemical signatures of things, they're not interested in going to the visible. They're actually interested in going to the longer wavelengths. And so the chemical signatures are far more, much stronger as you go to longer wavelengths rather than the shorter wavelengths. And so that's why the push is to longer wavelength rather than shorter wavelength. Mind you, for most of those guys, they care about being in the atmospheric transmission window, which coincidentally is also what you in biomedical, because you need to avoid water. In their case, it's atmospheric water. And in most biomedical applications, it's just plain water as well, basically. Yeah, so we expect by next year to have 5.5 microns, and then we've got a program hopefully to go out to 13.5, hopefully out to 13.5 microns, where a lot of the explosives and things like that have distinct signatures. Yeah, so we're not pushing short, we're pushing long. As I said, if you want to go down the visible, we can certainly do it, but also you can buy a NKT or Phanium laser to do it as well. I'm sorry?
Not for $1,000.
Our goal is to have I say this with, everything depends on volume, because when you're doing telecom parts, it's volume, volume, volume. But our goal is to have a commercial $2,000 laser in volume that goes from 1.5 to 2.5 microns. That's the size of, portable memory bank. That's our goal.
But
we think we can do that.
That price point going down to 700 microns, 600 microns, there's nothing out there that does that.
Yeah, the problem is that the photonic crystal fibers are all protected by the intellectual property, and what used to be crystal fiber got purchased by NKT Photonics, and so they can charge what they want for the fibers. The fiber alone costs $5,000 because they can, not because that's the actual cost of it. And so you're dominated by those guys that have NKT's intellectual properties, not so much around the superconducting lasers, we have that, but they have it around the photonic crystal fiber. And so that's why that price is, again, artificially high. But the other problem is there isn't a volume application. They're big application. Half of the market for superconducting lasers right now are on Leica confocal microscopes. But how many confocal microscopes are there? There's 100 a year, 150 a year. It's still not large by any reasonable volume of really bringing these prices down, kind of things. But the question is, if you can get in something glucose monitoring or something, you get a much larger market. Then you stand a chance of really bring the cost points down. But we think that if we can get superconducting lasers into the couple of $1,000s in the SWIR, then it really makes it so it's an add-on to, for example, the system that I saw Tim show me, or other systems of that sort, right? There would literally be yet another module, just like you have the spectrometer and that black box, it would be another module like that that goes in there. Probably, maybe twice the size of the tungsten halogen lamp. I don't know, I didn't see the power supply of it, but something like twice the size of that blue little cylinder that you have there. That's what we'd like to do, but again, it takes some volume to get down to that price point. Without the volume, I can build that laser today. This laser, to give you an idea of, and again, we build everything, obviously to customer, but the silver box I showed you, wherever it was, that's in quantity 1, that's a $14,000 laser putting out 5 watts. Quantity 1. By simplifying that design, well, that doesn't include labor costs and all that. I'm just saying all the parts cost or something like that, But I can tell you that, this laser parts cost is $14,000 quantity 1. I can get that down closer to, with 2 stages, I can get it down to, with any kind of reasonable volume, down to $5,000. With a single stage, I can get it down to $2,000. Simple. Again, there's engineering costs associated with that. But again, the thing is, because we're leveraging telecom parts, it really can be a game changer in terms of the cost. So NKT and those guys charge what they get away with. But we can build it much cheaper because you can see the designs are pretty simple. Just splice the fiber and go, kind of thing. But what really is needed for the volume, so it really comes down to volume, and so with the volume comes the need for a killer app. And so I can tell you, all of us in the field spend hours on end talking to people, what's the killer app for SWIR? Yes, the government wants it, but how many HSI systems are there out there? There isn't enough to justify developing of a whole field, right? What is the killer app for SWIR? That's sort of the, literally the $1 million question, or maybe $1 billion question. And if you can make it into breast cancer, that's you've got a huge market. So that's why we're very interested in breast cancer. If you can do collagen restructuring with tissue to do laser welding, that would be a huge market, because every medical procedure that that cuts tissue would be open to that kind of thing. So there are things that we can find one of those niches that's a large market. That's it. We know how to do the light source. We're golden. But there just isn't a killer app out there for the SWIR right now. And so, if you know it, please tell me. We'll go run and do it. but none of us know what that. I know how to build a light source, but we don't know what it's to be used for. There is not a killer app that's driving it. And then, if you had the killer app that had the volume, we can absolutely bring the cost down. I mean, I know Gordon's from the telecom space. He understands that, with volume, these things come down. The rule of thumb in optics for telecom is, with volume, the price goes down 30% for optics, 50% for electronics. And so, you're going to see these things dive in price and the other thing is, almost everything we're talking about here is used, the huge market is not this, but it's telecom and material processing. And so, you don't have to build this stuff for your application. It's being done already, because, when you get your cell phone and you get these 14 megapixel cameras, they can't use a saw blade anymore because it cuts more real estate than, the chip itself. So they literally use lasers to cut those chips. That's why that technology is being driven. And so if you can leverage that, but we got to find the killer app. So Bruce, if you can work with us to figure out what SWIR is good for, I'm finding a killer app, we're golden. but any of you know the answer to that question, please come tell us and we'll go to run and do it.
With that challenge in mind, let's thank Mohammed. If any of you have not had a chance to talk to Mohammed, please let me know. We can try to squeeze you in on the schedule.
Okay, hit the stop button, right?